Alright, so in this video we're going to be talking about how can we get a better return when we're compounding, and also how this compound interest stuff relates to E. So, given our formula, we know that the 500 on the outside means that's our starting amount. We have $500. Grandma gave us $500 and we're going to put it in the stock market. We have 1 plus given by the formula. We have 7% is our compounding rate. I chose 7% because that is the general return of the stock market. If you're invested in like some S&P index fund, we have 1, which means we are compounding every single year. In other words, apply this multiplier once a year, and then we're putting it in for 5 years. And we see here that we would have $701. Let's move down to the next one, because the next one is saying the only number we're changing is the compounding number, right? That's the only number that's changed. That means we're compounding every 3rd month. There's 4 sets of 3 months within the year, right? So we can compound what is known as quarterly. We're compounding quarterly, and we find that we would get about $6 extra because we're compounding much more quickly. Remember, compounding means when you apply your rate, your multiplier. Okay, so if I'm doing it if I'm doing it quarterly, I'm going to be applying more money to it. What happens if I do it monthly? Well, I get a little bit more. What happens if I do it daily? That's right, you guessed it, I get a little bit more. The more times we compound, the more times we apply our interest rate, the more money we make. Now, how does this apply to the letter E? So, little history on this. Bernoulli, mathematician guy, he was interested in compound interest. He was interested in this phenomenon where, hey, my money is growing as long as I'm compounding more often. But he was wondering, well, what if I was compounding instead of daily? What if I was compounding hourly? What if I was compounding every minute? What if I was compounding every nanosecond? How much money could I get out of this idea of compound interest? And he didn't work with what we know today as E. It was Euler, Leonhard Euler, who really took control of what E was and worked with it, figured it out, and all that fun stuff. So let's take a look up here. Oh, this is spoiling it. Okay, so let's go back, because we already know that our goal is to be compounding as often as we can. And so this is saying, let's compound daily. And I could put the ×1 up here because we're looking at what's happening every year, but I'm not going to do that. Okay? So I want to double this, because I want to say, instead of happening once every day, I want to know what's happening at twice a day. So 365 times 2, nope. Okay, 730. I'm going to do 730. And we get 2.716. That's pretty good. Let's go, just for numbers, let's go 1400. 1400. Again, why am I making these guys the same? Because this is our N. Remember, these guys have to be the same when we're doing our compound interest formula. But look at this, 2.717. let's add another 0. 2.718. Well, aren't we compounding even faster? Look at this. We keep compounding faster and faster. And what in the feezy? 2.718. Let's compound faster. 2. What in the world? This, my friends, is E. The phenomenon of no matter how fast you compound, you arrive at this number of 2.718, and it goes on forever. It's an irrational number, like pi, which also goes on forever. Pi represents a number, right? E also represents a number. It's not just a variable within mathematics. So no matter how fast you compound, you're always going to arrive at this number of 2.718 and some change. Okay, so this we call compounding continuously. If we compound continuously, we get 2.718, which is our E. So check this out. If I have E, Y is equal to E, we have a constant line at 2.718 because, again, E is an actual number, right? It's an irrational number, but it's a constant number. Just like if I were to graph Y is equal to 5, we see a constant line, boom, at 5. What if we put Y equals EX? Well, we get a linear, right? And what is our rate of change? Our rate of change is going to be 2.718 all over 1. Alright, so similar to the exponent rules of solving that we had when we have two bases that are the same, we can use a log function, log base 4, to cancel out both of these 4s and just work with the exponents. We can do the same thing with E, but instead of using log, we use what's known as the natural log. The natural log, of this guy. These will cancel out. Boom. And we're left with just the x plus 2. But I don't think Khan Academy has you do problems where you're using E and natural log to cancel things out. But I feel like I'd be doing you a disservice as a math teacher if you didn't ever know about natural log and E. So the last thing I want to show you is the natural log and E working together, because the same idea of exponentials having an inverse, which is their log functions, E also has its inverse has an inverse, which is the natural log function. So we can see here the classic inverses are going to be mirroring that y is equal to x, and we can confirm that natural log is indeed the inverse of e to the x.